right, so before we get going on anything new, since it's been a long weekend since we last talked, I just want to quickly recap what we talked about here and then progress forward. So our goal, the reason we're dealing with all this nonsense, which this, as you know, gets really tedious quite quickly, our goal is to be able to take a rate of change function, like a velocity function like this one, or something that tells how fast something's changing, whether it actually relates to time or not, how much one thing changes with respect to another. Lots of times the second portion of that is time, like whether it's dollars per day or people per year or something. But it doesn't have to be per time unit. It can be other sorts of things as well. And we'll see some examples of those. But our goal is to start with some sort of rate of change function and be able to estimate, even though it's not one constant rate of change, be able to estimate using a bunch of, well, constant rates of change for small amounts of time, in this case, for small intervals, and then getting an estimate based off of using constant rates for what happens due to those. So this velocity function on the left, the curve is the exact rate of change of the height, and the horizontal line segment sticking out of it, that's a second function. That was our approximate rate function that we were using. And you don't have to draw a picture of that, but what we were doing was using individual values from the exact rate of change function every so often. And we picked it at a regular interval so that it was easier to keep track of. So you can imagine just using the rate at 0. This was using delta t equals 0.9 seconds. This parameter delta t was just, chosen out of my head because I wanted to pick something. So we could see where the 0.9 played into it. 1 sort of disappears. So from 0 to 0.9, we're going to use 1 rate. Even though I know that this rate of change, the velocity of this rocket-powered basketball was actually increasing, we'll use 1 rate for a little bit, and then after 0.9 seconds, we'll use the exact rate again, and then see what would that do over 0.9 seconds. What would this next rate at 1.8 subbed in for t, what would that rate do in the next 0.9 seconds, and so on, so that we can generate accumulations in height. So over each individual interval, we've just got a MDX sort of expression to compute the change in height. And if we add all of those together, we get the cumulative change in height, or the net change in height since, in this case, time 0 when we started. We don't have to start at time 0. It doesn't have to be this rate function. We don't have to use 0.9. Those were all just choices for this particular question. And the other thing that was just a particular thing, this t equals 5, that was just so that we can stop somewhere. But our overall goal is to be able to take any exact rate function and generate an approximate accumulation up to any numerical value we want, or in fact just to generate an approximate accumulation up through a time x, so a function for accumulation, so that I could just write it in general and then plug in any number for x, like, or t, whatever it is, like 5, later after I write the function, and it would do all the computations for me. Because if you can do that, which is something that you could type into GC, then you know that you've got something that represents this approximate accumulation. Now, that's kind of like 90% of our goal. Because in reality, what we'd want is an exact accumulation function. But if you can imagine, the only difference between having an approximate accumulation function and an exact accumulation function as a result would be, well, how do I do this? In this, using delta t equals 0.9, I can see this is a really rough estimate. But what if I were to use delta t equals 0.0001? Well, that's probably going to be indistinguishable from anything with delta t equals anything smaller. So I could say if I use an extremely small delta t, especially in the case of some rate function like this where there's not rapid changes in steepness, it's just kind of a smooth, not polynomial because it's not a whole number, but it's a power function curve. Nothing unusual happens in it. So if I make delta t extremely small, I'll get an extremely accurate answer. And this delta t was just a parameter here of 0.9. If you know how to write an accumulation function with 0.9 as the interval width, if you just change the interval width, that's not really changing too much of it. In fact, if you were writing this in GC, that would change one line, just where you define what size delta t is. So, and then everything else would be computed, and you get a much better answer. Well, in fact, if you look at this height function here, even from my distance, I'm the closest one to it in the room, it looks pretty much like a smooth curve. The only idea, if delta t were a little bit smaller, I know that over this first 0.9 seconds, the rate isn't actually 0. It increases a little bit. So between 0 and 0.9, my height should actually be not staying at 0. My height should be going up a little bit. So this is all an underestimate here of the actual accumulated height during this interval, because all of these approximate rates that we're using are only exact at their left endpoint, and then they're underestimates all the rest of the way. So we're underestimating the height achieved by this basketball. But other than that, we can probably see, yeah, it's going to be something like this pattern, but A, smoother. There's not going to be any corners to it because there's not any sudden changes in the rate in reality. We made those extremely sudden looking changes from one height to another, and it actually still looks pretty smooth. So we can maybe see that the actual exact accumulated height function would be pretty much like this, but maybe a little bit higher, a little bit steeper, because all of our rates are a little too low, with the exception of the left endpoints. So in any case, what we did for this specific problem with all those numbers in place, if we wanted to figure out how much height was accumulated during, let's see, the first 5 seconds, we said there was 5 full intervals plus part of one more. And the 5 full intervals, we can say, well, it's 5 seconds. How many 0.9s are there in 5? It's just a division problem. There's 5 of them with a little left over, because 5 0.9s makes 4.5 seconds. So this, which is just a series of rate times delta t, a different rate times delta t, a third rate times delta t, a fourth rate times delta t, a whole bunch of exact evaluations of our velocity function times the length of time for which we use it. And the upper row then is the symbolic way we could write that. The lower row would be specific to this particular rate function. But all of those are pretty similar terms. They're all just evaluating a rate function times delta t. And in fact, even the numbers inside, they had this nice pattern. So the only part that changes from term to term is, well, let's see, how many 0.9s have we gone through? So there should be a way that we can kind of describe that in general. In fact, even with the current interval, that little piece left over, it's also just this exact rate function evaluated at one more point. That's another multiple of 0.9. And then, well, times something different. So what we jumped to after this was we did a quick review of how summation notation works, because what I'd like to be able to do is write all of this in 2 terms, really. There's that one stray term from the current interval. It's too much different from the other. It's got 2 things differently. It's got a different input for the rate, but all of these have that. But it's also multiplied by a different number. And that number depends on, well, where this is relative to the end of the interval. So that last term's a little bit messy, but the rest of them, here, let me just skip past this. The rest of them, we should be able to write with some sort of sum. And again, our goal, we know how fast a quantity's value is changing at every moment, or we know a rate of change, and our goal is to know how much of it we have at every moment. So I'm going to move away from the basketball and just talk about some generic rate function. So actually, I've got a moving picture of this. I want to talk about the moving picture of this, and then we'll think about how this is kind of a generalized version of what we were just doing with the rocket and the basketball and the 0.9 seconds and all that. Let me open up a GC file. Here we go. So this one plays very slowly. So you can see if I have this exact rate function, r sub f, and I've used approximate rates every so often. Notice every so often is a different every so often than the example with the rocket basketball. It doesn't have to be 0.9. That was just random. In fact, maybe you can see what I have up here. I have delta x equals 1.5. So I'm using each exact rate for 1.5 seconds at a time, 1.5 units at a time. This one isn't specifically a basketball. I don't know what this is. This is just some generic wavy curve so we can talk about, in general, how this process works. But you can see as x increases, as we start from, in fact, we started the rocket basketball at time 0. We don't have to start at time 0. And in fact, if you remember the lawn mowing question, there was some weird stuff that happened at the beginning, but after that, we knew what the rate was. And in that case, it was a constant rate because we hadn't gotten to this stuff yet. We had a constant rate that applied after a certain point. Well, even if I just have a known rate function, this red r sub f, that applies after a certain time, and I'm going to use that. I'm just going to talk about what happens net accumulation-wise, whether it's net change in height or distance or money or population or whatever it is, starting at time A. So this lowercase a is going to be when we're going to measure the start to our accumulation. So I picked a random point that, well, not too random, it's just 0.5. And then using exact values of the rate function every 1.5 units after that. So I'm going to pause this for, let's see, after the third interval starts. So you can see if a is at 0.5, I would use this one value of the rate for the next 1.5 units, so up to 0.2. And then I use this next value of the rate from x equals 2 for the next 1.5 units up through 3.5. So I have these little red dots on the axis here that are kind of for, well, I don't know, for my reference at least, but maybe you can see them. But that's how, every time we hit one of those red dots along the x-axis, that's when we're starting a new interval. So you can see there's an interval from 0.5 to 2, from 2 to 3.5, 3.5 to 5, 5 to 6.5, and so on. But if I were to change delta x, it makes kind of more of a mess of this, because right now I'm almost at the end of that second interval. Doesn't work out so nicely if I have weird numbers. But it's the same general process, where I have some intervals that are full and I've used one rate for the full 1.7 now, and others where I haven't. And I can change a also, doesn't matter. Let me make delta x 0.7, and I'll make a 0.2. That might squish the letter into the axis, but we'll see. Not too bad. But all this does is change the setup to this, and you can see maybe the smaller this delta x is, the less far away these horizontal lines, these approximate rates that we're using as a constant for a while, the less far away they get from the actual curve. I can make it really, really small, and this will be hard to see. But you see, like, all these little red dots are really close together now. So the idea is, let me just move this somewhere here. I have some bizarre length of whatever now. So starting at 0.2 and measuring accumulation using an exact rate every 0.7 units. Just two parameters that were chosen for who knows why, just because I made up those numbers. But this is not showing what happened because of the rate. This picture here just shows the rate of change function and how we're using pieces of information from it. So I've got several complete intervals or completed intervals, ones that the current x value's already passed. And then I've got this stray current interval at the end, or just, you can call it the leftover. It's the part that for any value of x, there's a potential that you aren't at a boundary point, and we're not. You can see this is kind of smack in the middle between two interval endpoints. So I've got a bunch of completed intervals, and I've got one interval that I'm in the middle of. So if I wanted to express what had accumulated due to this rate, and this is all positive rates, so I don't have to say like de-accumulated or make up some kind of word for that in general, which is weird when you don't have an actual context. But if I wanted to talk about this, I need to figure out how do I evaluate the rate in each of those intervals that are complete. And even in the current one, it would be the same sort of pattern. I'd use the rate from the left side of that interval, just like you use the rate from the left side of every interval. And then I'm going to use each of those rates, except for the last one, for 0.7 units. So I do at MDX, multiply each rate times 0.7, and so for all the completed intervals, that's just one big number. For the current interval, it depends on exactly what x is, what I multiply by, and I could even express that in general based on, just a generic x that I happen to know is in the, I don't know, I'm just going to say number 12th interval. If I know there's some value of x between the beginning and end of the 12th interval, then I'll do that distance into that interval times the rate at the beginning. So the difficulty here is that I hope you can kind of see what the general process is. Oh, like, well, in the context of distance, like rate times time, a whole bunch of different rate times time. In this case, it's a whole bunch of different rate times, I don't know, length of delta x. But I want to be able to express this in general. So there's two main tricky parts to this. A, how do I say in general how many full intervals I have? That's kind of a weird process. Like, how would I describe for a generic x how many delta x's fit before that? And second problem would maybe be, well, how do I say in general for any x how far it is into the current interval? That's also sort of a weird one. So we're going to come up with some ways to write that. That's what we're going to spend a lot of our time on, but we're talking about this whole week. We're going to do a lot of exercises and kind of understanding the notation to make sure that we're okay with what's going to be kind of a messy sum. Let's see, which one was it? Oh, I know. Got a bunch of things up here. But we're going to have something like this by the time we're done. F of x, or actually I should call this a sub f of x, the accumulation f. I don't know what it started at, might not have been 0. I'm going to have a sum of a whole bunch of rates times delta x, plus then one stray term that has, again, a rate, but this dx, how far I am into the current interval. So why I said dx here, if you remember that like kind of MDX expression, we're wondering how far x has traveled since we started using this rate. These are all fixed. These are already done. I know the length of all of those intervals. This is the only one that's possibly still moving. If I vary x a little bit, this part's going to change, and this part's going to stay the same. So I'm going to use this dx, which is a variable in this term here. And delta x is just a parameter, stands for a single number. And when x varies a little, this part, unless it varies too much, and we go into a new interval, if x varies just a little bit, this part's going to stay identical. All the completed intervals are still completed. They're not going to uncomplete. I'm not going to get new complete intervals. This part is the term that's going to change as x increases by just a little bit. And what's going to increase is how far x is from the beginning of that interval, how much I'm using the current rate for. All right, so let's go back to a slightly more numbers sort of question, but it'll be less of a specific example than the rocket basketball. Let's see. There we go. All right, so here's our picture that I showed you before. Let's say that I wanted to talk about how much accumulates between x equals a and x equals 6.75 based on this picture. Now you can't really see, I don't have listed here what the delta x is this time. If you can see these red dots a little bit, we're starting at a equals 2, and then, or a equals whatever that is. I guess it's a little bit past 2 is where that is. But you can see, oh, there's 1 full interval, 2 full intervals, 3 full intervals that are delta xy, and then 1 leftover piece. So in terms of trying to find this value of what accumulates between lowercase a, the beginning of where we start being able to use this rate of change function, and mystery point 6.75, so not generic x, but just something in specific, I can count how many full intervals there are. So I can see on here, there's 3 full intervals, and then 1 leftover part that seems to be a different length. We're in the middle of it somehow. So it's not exactly at 2 and 3.5 or something like that. They're kind of unknown numbers, but this first interval starts at a, because that's between x equals a and something else. So we're going to start using a rate at x equal to a. What would be the exact coordinate point for this spot on the red curve or the horizontal line segments, either one? A comma, yeah, r of a or r sub f of a. It's the same point because the horizontal line segments, the approximate rate and the exact rate are the same there. So I can call that either r sub f of a as the y coordinate or r of a. Either one is fine. And that would be the rate then that I want to use for this first interval. R of a times delta x, which I don't know what delta x is, but delta x is how wide that full interval is. This rate applies for a full interval because I know that in this picture 6.75 is past it. So we've got 3 complete intervals and 1 stray part, but r of a would be the rate in the first interval. Now, how could I express the rate that I use in the second interval? Comes from being 1 full interval past x equal a. What would be the x coordinate location of this red dot here, where the second interval starts? Yeah, a plus delta x. So I started at a, and then I moved delta x, 1 full interval width, to the right. So the x coordinate here is a plus delta x. So the rate that I'm going to use for this next interval is going to be the rate at a plus delta x, which I can express either r or r sub f, either one, but at a plus delta x. So the stuff inside the parentheses is that x value location, but r of that, or r sub f of that, is the rate that we're going to use for the full interval. What about for the third interval, the one that kind of currently has this delta x written over top of it? A plus 2 delta x. Because, yeah, so this location here is a. If I go to the right by delta x, I'm at a plus delta x. If I do that again, I'm at a plus 2 delta x. And even the current interval has the same pattern for the x coordinate at the beginning of it, be at a plus 3 delta x. So this is the kind of more general pattern for how these are going to work. Wherever we're starting a. In the rocket basketball question, we started at 0, because that's when we launched this, and it had this velocity starting at time at the beginning. But starting at any point, lowercase a, I can measure accumulation starting there by finding the rate, exact rate of change every so often after that. So starting at the rate at a, the rate delta x later, the rate 2 delta x later, 3 delta x later, and so on and so on. So those are all the rates we need. And each of the complete intervals, we use that computed rate for a full delta x interval. It's only for this last one that we have this kind of stray, like, well, and whatever this is. And then when x varies within this current interval, this part's going to change, but those 3 labeled with purple, those aren't going anywhere. Those are staying exactly the same as long as x is somewhere between this red dot and that red dot, somewhere within this 4th interval. So I've got 3 full intervals and 1 with a little bit of leftover, 1 of a different length. So I'd like to be able to express those 3, which are fairly similar terms. The only one part that differs between them is what's the input to the rate function, what's the x value, or the independent variable value that we use as the input to this rate function. In one term it's a, and then it's a plus delta x and a plus 2 delta x. I'd like to find a way to write that just by, substitute in the numbers 1 through 3, and magically this comes out to be the expression that I want. This is one of the tricky looking parts to this because it looks a little bit of a mess. But just kind of thinking about this a piece at a time. And again, remember, this is a lot of little details here and there. Overall goal, write an accumulation function. How much has happened? The trickiness here is how do I express in general what's going on in those complete interval terms? So I've got 3 intervals. In the first interval, or thinking about substituting in j equals 1 to this summation, I want it to come out to equal a. In the first interval, I'm using r of a, or r sub f of a. But when I substitute in j equals 2, I need it to come out to look like this. And when I substitute in j equals 3, I want it to come out looking like that. So looking at the first term is maybe a little bit confusing, but looking at these second and third terms here, you can see, like, how could I substitute in 2 and make it come out a plus delta x? 3 comes out a plus 2 delta x. Maybe this one's more obvious, like, oh, well, I want to sub in a 3 and somehow get 2 delta x, 1 less delta x than whatever j is. If I sub in a 2, I want to get 1 less delta x, 1 delta x instead of the 2 that I'm subbing in. When I substitute in 1, I don't want to have delta x's at all. I want to have 0 delta x's. So it's a little bit messy, but if I'm in the jth interval, first interval, second interval, third interval, I've got, well, a plus a certain number of delta x's, but how many delta x's I have added on is 1 less than the interval number, 1 lower than that. So the expression that I actually need in my summation is r of that mess. R of a plus 1 delta x, r of a plus 2 delta x. The number of delta x's that I have added on is 1 less than the interval number that I'm on. So interval number 1 has no delta x's. Interval number 2 has 1 delta x. So when I sub in a 2, this j minus 1 gives me a 1. Interval number 3 has 2 delta x's, 3 minus 1. So putting this together, tedious work with sums and how do I get this to do what I want? I want it to increase by number of delta x's each time, but the interval number and the index number are off by 1. Or the interval number and the number of delta x's number would be off by 1. So here's the expression for those completed intervals that we're going to have all together. So this is specifically when we had 3 full intervals, so j equals 1 through 3. Here's our rate evaluated at that expression, a plus j minus 1 delta x. So all the stuff inside the parentheses indicates one of those red dot points. An a plus delta x, a plus 2 delta x, a plus 3 delta x. This delta x out here is the other part of the expression, because to measure accumulation, we do a rate times an amount of time that we use that rate for. So this is all the rate, this is the m, and this is the dx. So m dx, that rate times time sort of expression, this is the times time. We're using delta x twice, one to determine an x value that we're at along the x-axis, and one to multiply by our rate. So that's why we see it twice here. I wrote it smaller inside so you can, they are 2 different ones. It's not delta x times delta x. I've got a rate times a delta x. So if I were to substitute j equals 1 through 3 into this expression here, I should get those first 3 terms written up above. R of a times delta x, r of a plus 1 delta x times delta x, r of a plus 2 delta x's times delta x. And again, all these things inside the parentheses by the r, or r sub f, doesn't matter, they're the same, at those left endpoints. Those are all rates at the left endpoints of intervals. So this is one of those sort of messy to write expressions, but keep in mind again what we're trying to figure out what happened because of our rate. So we used a bunch of rates, multiplied it by how long we used it for. It's just, how do I write that in general? Yeah?
So inside the parentheses, the delta x is for the individual interval, and the outside is for the entire thing?
So inside here, this a plus j minus 1 delta x. So this a plus delta x, a plus 2 delta x, those are representing, they're inside parentheses in a function. So those are representing x values or x-axis positions. So this is, let me go back to the picture. Let me do this. Maybe this one. Well, I'll do it on the GC file then. So each of these red dots here, I'll make the delta x a little bigger. Oh, this isn't a file we actually looked at before. This is a different one. But same thing. There we go. I'll make this delta x a little bigger so it's easier to see. So this is position A, this is position A plus 1 delta x, A plus 2 delta x, A plus 3 delta x, A plus 4 delta x. And so when I substitute in any of those into the rate function to find a value, to express the y value here, where the horizontal and the curve match up, so the rate value that I'm using at this spot, and then I just continue using it for the full interval. The rate value here, or the equation of that horizontal line segment, would be y equals r sub f of a, or y equals r of a, either one. But the height here is r of a, the x-coordinate's a. If I'm looking at this one, the x-coordinate would be a plus 1 delta x. So a plus delta x is this spot on the x-axis. And the y value here is r of a plus delta x. And then this is the height here is, so I'd read it off over there, would be a height of r of a plus 2 delta x. This spot is a plus 2 delta x. The height here is r of a plus 2 delta x, or the rate.
So if you're about 3 intervals in or so, does that mean that the one outside is the combination of all the ones before it also?
Well, so this graph doesn't show cumulatively what's happening anywhere. This is all just rate graphs. So this is just looking at the exact rate function, this curve, and the approximate rate functions. I'd need a second graph to show what happens because of those rates. But if you want to imagine for the first interval, I've got this rate of, just looking at numbers, rate of 0.5 that I use for 1.8 units. So starting from this a value, if I were going to say what happens because of that rate, a rate of 0.5 for 1.8 units, that gives me 0.9 of whatever it is accumulating. 0.5 times 1.8. So I'd have 0.9 accumulate from 0 up to 0.9. And then in the next interval, I have a higher rate. So for the next 0.9 units, I had accumulated a faster rate. So it'd go from that 0.9 up faster to the next amount of accumulation by the end of this interval. So this graph here only shows rates. It doesn't show what accumulates. It doesn't show the value of this.
I was actually wondering what exactly you meant by the 2 delta x's are going to be different values or something.
Oh, so I can change delta x to have different values, but so in this graph right now, as it's pictured, those red dots are 1.8 units apart. That's how often I'm taking an estimate value off of my exact rate function.
So then the delta x inside the parentheses is just talking about the interval that you're currently in?
No, delta x is a parameter. It has one value throughout the whole problem. So now it's 1.2. And as 1.2 inside the parentheses, it's 1.2 outside the parentheses. But in terms of this computation, inside the parentheses, a plus however many delta x is talking about an x location, and this times delta x, the reason I'm multiplying it onto a rate times something would give me what happens because of that rate. So they're used in different ways. One's to pick out a value for the rate function to use, and the other's the how long I'm using it for. But it's going to be delta x in both places because of how we're doing this, because every single time Yep. Every single time, I want to be using a rate from the beginning of an interval and then use it for that full interval. And since the intervals are spaced delta x units apart, defining where they start and stop involves delta x. But then I'm also using them for delta x units. And using a rate for delta x units means I'm going to do a rate value times delta x.
So we're double checking. We're
yeah.
writing that out. The two delta x's are going to have the same value.
Mm-hmm. Yeah, so the two delta x's have the same value for any specific problem. It's a parameter that you can pick at the beginning. When we were doing the rocket basketball, it was 0.9 seconds. When we were dealing with the oil spill, it was like 0.3 days. It's just a parameter, and that determines how often we go to find a new rate value, and then also it defines how long we use the one rate value for. Those are going to change at the same positions. Those have to match for that reason, because of how we're setting this up to use one rate for a full interval, and we change rate values every time we change intervals. So this is not easy. There's a lot of symbols. It takes a while to kind of put this together, but just keep in mind we're doing like a whole bunch of rate times time, or a whole bunch of MDXs added together is our goal. Question? What does J represent in this context? So J doesn't have a meaning in terms of this function. What J is doing, it's kind of like a counter. So I wanted to add up 3 full intervals worth of stuff. And so each of those first 3 terms is pretty similar. It's just different by how many delta x's there are inside the rate function in terms of the x value where we're evaluating. And so what we did is create a new variable for that. It's called an index for the sum. So on its own, it doesn't have a meaning. Like J isn't like the number, like the height of the basketball or something like that. And it's not something that we graph. But you can think of it as interval number. So J equals 1 through 3, that's talking about figuring out what happens in intervals 1 through 3. So if I substitute in J equals 1, I get the accumulation during the first interval. If I substitute in J equals 2, I get the accumulation during the second interval, and so on. And if I add those all together, I get the cumulative accumulation during however many I've added together. So 1 through 3 is the most I could add together here because, well, this problem was just, we only had in the picture, this was just from looking at the picture. You can see there are 3 full intervals. So we'd only add up 3 terms that were identical in length like that. 3 terms that were this delta x, which seemed to be, I forget, like 1 point something units long. And then multiply each one of the rates times that 1 point something units, times that delta x. So we have this expression. This is the written out term by term. And here it is, the first 3 terms we can write this way. If I want to know the total net accumulation since lowercase a, since the starting point, again, lowercase a is just a parameter. Let's start at a. Let's start at 2 seconds in. Let's start at 3 days in. Let's start at, it's just where we're going to start using this rate from. There are 3 full intervals, and this one summation can cover all of that. Now maybe you can see if this graph were to go on longer and I had 10 full intervals, all I'd have to change is that number on top from a 3 to a 10, and I'd have an expression for that just as well. So once I have the general setup, I can adapt it just by tweaking individual numbers or symbols here and there to make it represent something different. So that's why we're working on trying to generalize this process so that it doesn't have to do with, well, 6.75 specifically or this curve specifically. The 3 is specific to this picture and how you can see 1, 2, 3 full intervals. But if it looked different and there were 17 intervals, all I do is write a 17 here. And it would do the same thing. That last one would be a plus 16 delta x's to get to the beginning of the 17th interval. All right, so what we don't have expressed quite so nicely is this one here, but it's not as similar to that term. It's got 2 pieces different from that, but it's somewhat the same. I've got a rate evaluated at the beginning of an interval again. It's the beginning of the most recent interval. If this was 3 intervals there, then this is the rate at the beginning of the 4th interval, which is a plus 3 delta x. We could still use j's, but we don't need to because we're not trying to throw it into this summation. So I'll just call it r of a plus 3 delta x, or r sub f. Again, r and r sub f are interchangeable right now because they're all just talking about the places where they're identical, those left ends of intervals. But this dx, there's got to be a better way to express that, because dx is just kind of generic. It doesn't use this 6.75 at all. So I'd like to be able to say, well, whatever my actual current value of x is, how do I figure out dx? That is, how far is this current x value from the beginning of this interval that I know I'm not all the way through? It's not delta x. It's something smaller than delta x. But how would I express that? And I think we did that in some earlier expressions when we were writing out the piecewise functions. If you think about when we were trying to write out the piecewise functions, every time we got to the O, plus however far we are into this interval, however far we are past the left edge of it, whether it was at 0.3, 0.6, 0.9, or whatever it was at. So this dx is the only other piece we really need to worry about changing to have a way to express kind of something more specific, because dx isn't a parameter, it's a variable, but it's not like, how do I compute the length of this? I can do it based on x and the position of that most recent red dot. So just as a note here, I don't know how many completed intervals are there to reach the current interval. Well, in this picture, there were 3 complete intervals to reach this. Notice that this current interval has this 3 delta x. The number of delta x's in this matches the number of complete intervals. So this stray extra term is always going to have that feature. Like if there are 17 complete intervals, this would be a plus 17 delta x. Like I said, the one before was the minus 1. This one is after those complete intervals. It's the 18th interval or whatever, but it's not complete anyway. But just in terms of this a plus 3 delta x, if you're looking at this and say, oh, this must be, there are 3 complete intervals to the left of it, or x has passed 3 full delta x's to get to here. Started at a, went past 3 delta x's to get to the beginning of this current interval. So if you do see an expression like this, how many complete intervals are there before this current interval? It's that number in front of the delta x. It's got to match because of the way we've set it up. So there are 3 full intervals to the left. This is the 4th interval, but it's not complete. Because if I wanted to express it with j sort of things, it'd be j minus 1. This is in the 4th interval, but just notice this also means there are 3 complete intervals to the left of that, which that's actually useful. Because sometimes you don't want to count them up, but it's the same, however many full intervals you have, that's how many delta x's would be added onto a to get to the beginning of this partial interval, this current or incomplete interval. So all of them. So if I want to express this kind of in general, it's not always going to be 3. It's going to be a plus however many complete intervals there are, delta x. So that other GC file that I had pulled up a minute ago, if I can find this. All right, so just thinking about how these computations work. Think about this lowercase a again is where we're going to start accumulation from. Parameter, in this case, I gave it a value of 1.3. And delta x is 0.62. And what is this n doing here? Don't really know. Oh, that's just showing where we are. So we could generate approximate rate functions and all this, but if I want to know, so n here, that letter standing for the current value of x, it's just really small down below, 5.93. If I want to know how many complete intervals there are, like if you're close enough, you might be able to count like 1, 2, 3, 4. But if I said, okay, n is 5.9338, or x rather, is 5.9338. That's just this scooting along. We started accumulation at 1.3. We're using intervals of width 0.62, which if you're doing this, doing some computations by hand, that would be awful choices. But just thinking about, if I want to know how many complete intervals there are between 1.3 and 5.9338, if their width is 0.62, what computation is that you need to do? Yeah. Yeah, n minus a, or x minus a. And then, well, what was after that? Divide by 0.62. So, yeah, we find that how far apart they are, and then divide it by the interval width. And we'll get some weird decimal number. Here, I'll give us another line here. So if I did, let's see, 5.9338 minus 1.3, that's how far apart the current value and the starting value are. They're 4.6 something apart. So if I want to take that and divide by the interval width, 0.62, I get 7.47 something something. So if I want to know how many complete intervals there are, how many complete intervals are there? 7, right? You're going to round down because 7.47 isn't a complete number of intervals. Now, what if I made x just a tiny bit bigger? Let's see if I can do this. There. So that the current value of x isn't 5.9338, but it's 6.1025. And I do the same subtraction. It's subtract from a, or subtract a from it. So I find the distance apart, almost 5-ish, and then divide by 0.62, and I get 7.746. How many complete intervals are there? There's still 7, even though this is closer to 8. It's 7 and more than a half of a unit, or more than a half of an interval, but it's still only 7 complete intervals. So if I want to count this, no matter whether we don't want to use traditional rounding. We want to round everything down. And there's a math function for that you may or may not have ever used before, but it is a standard math function found in lots of like science textbooks sorts of things. I want to round this down to the closest whole number available because I want to have a whole number sort of answer to this, but I don't want traditional rounding where I could potentially round up. It's called the floor function. What floor does is take any result and it'll round down as opposed to, so it's essentially like truncating. You truncate off any extra decimals beyond so that you get just a whole number. So in GC, the floor function you get by just literally typing the word floor. I'm going to do it on a separate line here, but if I type F-L-O-O-R, the second I type the R, it's going to give me some symbols. Those are the symbols, those kind of brackets with just the bottom, that tells me I'm doing a floor function. And what I'm going to do is copy and paste this so that I don't have to type it again in there. And this rounds that result, as you can see, to just 7. You can type directly in there, just like you can type inside parentheses. They always come in pairs. There's also a ceiling function. We just don't need it. It rounds everything up to the next whole number. But this function here allows you to express in general, always round this down. No matter how this comes out, round it down to the closest available whole number. So this floor function will do that, which is handy if I want to describe how many full intervals there are. Because no matter whether I have 0.1 of an extra interval or 0.9 of an extra interval, that doesn't count as a full interval. I just want the whole number part in front of the decimal. So this function will tell us that whole number part, this floor function. So if in general what it is that I'm doing is, let's see, we took the x value, which was represented by n here, minus the a value, which right now 6.1 and 1.3 is where this is coming from. And then I'm going to divide that by delta x. Let's see if I'm going to have to copy delta x, I think. Okay, let me do this again. N minus a divided by. Delta x is kind of a hard one. That's one of those things that's difficult to type in any in any computer, and you might have seen notes about this, you'll have to use a different symbol for it if you have a Windows computer, because it won't do a delta, and I don't know why. Nope, that's not where I was trying to paste that. There we go. So here's the over delta x with, since those are all defined values, if I change n, this is going to, I'll leave it at 2 ways. If I use this slider, I can see this is just telling me the decimal format of how many intervals there are, 11 point something, 12 point something, and so on. If I want to know how many full intervals, I'm going to type floor in front of this. Actually, let me just do it, like I said, in a separate line. Floor of that. Copy, paste. As n varies, both of those vary, but the one above, you can see, just keeps growing in between, and the one below only jumps to the, from integer to integer to integer. So, unfortunately, I don't have n set up to deal with all of these values, so give us weird negative numbers at first. But in any case, you can see that that floor function gives you the number of full intervals, where this n symbol that I'm using is just for my slider x here. So it's really x minus a over delta x, and a floor function will give you the number of complete intervals. For no matter what x is, no matter what a is, no matter what delta x is, I could change all of those and this would still give me the correct computations, which is the sort of thing we're looking to do. We want to generalize this process. I don't want it to just work if delta x is one particular size and it's one particular function. I want this to work all the time. So if I want to talk about a plus how many complete intervals there are in front of delta x to get that expression there, because this one's going to be left out of the summation. So I have to find a way to write it on its own, and I could write it that way for this problem, but 3 isn't always the right number. It's a different number depending on how many complete intervals there are. And how many complete intervals there are? Oh, x minus a over delta x floor function. So that's the number that I'm going to put into this leftover part. And where else does 3 appear in this problem so far? 3 was specific to our example. 3 appears here, and it also appears at the top of the sum to tell us how many complete intervals there were. That 3, if I want to generalize and talk about not just this problem, but any problem, is also going to be turned to that x minus a over delta x floor function. So there's one other piece that's kind of nice to write because this is really tedious. So let me see if I can get this to work. I'm sure it's not going to at first. It'll take me a few button pushings here. This, play again, that. All right, so the total number of completed intervals is something that I am going to need to write here. I'm going to need to write here, and I'm also going to need to write here, and this is not cooperating with me. But the total number of completed intervals in this specific example was 3. It can also be this x minus a over delta x floor function. Now, just because this big expression is really, really annoying to write, we created this function. We're just going to use this. You can define this for yourself. This is not a standard in every math book sort of thing, but as long as we define it, we can use it. So we're going to make up this function to kind of shortcut writing all of this all the time because it's awful. As long as you understand what it means, it's okay. We're going to use left of x to indicate, well, the x value that's at the end of the current interval. So wherever x is, left of x is like a different sort of rounding function. It doesn't round like the floor function to a whole number. It kind of rounds you back to what's the beginning of the current interval. So to find the total number of completed intervals, we do this, which is a rounds to the next lower whole number. This left of x is a second rounding function that we just made up, and we just called it left because that describes what's going on. If I want to talk about what's left of this, which is x equals 3, oh, it's that x value with the red dot. What's left of this current x here? It's that one. So for every x value, there's only one value of left of x. It's this x value at the start of the interval we're currently in. You don't have to use it. It's an auxiliary function that's just kind of short to right, but it's nice because it's short to right, because as you can see, this kind of trying to generalize this and make it cover all possible functions with all possible delta x's and a, lowercase a's and capital A's and current x values. That whole expression in brackets a plus x minus a over delta x floor times delta x as an input to a function looks kind of horrendous. So r of left of x, which we can only use once in this function because it has, for any x value, it has this one value. It's a function. For any x value, this gives us another x value. We're using it as an input to a rate function. But left of x is kind of strange in that way because it's a function that takes any x value and gives you a different x value. That's the left end of the interval your x is in. So similar to how this rounds down, this kind of rounds back to the left. It rounds to the left end of the interval to tell you what that current interval's left end x value is, which is exactly what we want when we want this stray extra term. I want the whatever interval x is in, I want the rate from the left end of it, which we could express in this other sort of way also. This is the short way that will allow you to write it, because we're going to define this left of x and use it throughout. Like I said, it's not the floor function. Every math textbook knows what that is. Every math teacher knows what that is. It's not discussed in every math textbook ever, but it's a standard math function. Look it up on the internet. Left is kind of something that we're making up for us so that we can say it succinctly, but what we mean by it is this left end of our current interval. So if I want to talk about not anything specific with the a of 6.75, the accumulation from lowercase a through x equals 6.75, if I want to talk about accumulation in general from lowercase a up through general x, so that I have, in fact, by the time I'm done, a function, capital A of x, the net accumulation starting at lowercase a and going through any value of x. I'd have accumulation due to however many complete intervals there are, plus accumulation from the current interval, which we'll just use r of left of x. And we're going to go over this again. I'm going to give you some questions to think about. I'm going to go over this again on Thursday, this kind of putting all this together part, because I know there's a lot of symbols here, and it's a little overwhelming at first, but this is our, almost our last goal for before your test, which is a week and a half from now. So we've got time to practice some more, answer some more questions, work on some things, think about it, digest. But for all the complete intervals, I have these rate functions times delta x, the rate at the next beginning of an interval times delta x, the rate at the beginning of the third interval times delta x, and so on for however many intervals there are. Plus, wherever I leave off, however many intervals there may be, however far I want to go, there's always going to be a left end of the current interval, and I'm going to use that rate for a little bit more. And I mentioned this earlier, but we didn't quite get there because we got hung up on the how do I figure out how many full intervals there are. But this, how far are we into the current interval? Well, it's however far x is past the beginning of the interval, however far x is past left of x. How do I figure out how big that is? Subtract. So the how many completed intervals was this floor function. So we did 1 through 3 before. There were 3 complete intervals. We're going to do 1 through that x minus a over delta x floor. to get the number of completed intervals. And then this is an extremely generalized, covers every situation if I know a rate function. And again, I could have R or R sub f, exact rate function or approximate rate function. They have the same values at points like this, at those interval boundary points. They have the exact same values. So I'm going to add up rates times delta x. How many of them? Well, how many complete intervals are there? How far is mystery x from A in terms of number of intervals of with delta x? Find the distance divided by delta x and round it down. And then this accumulation in the current interval, or the partial interval that we've got at the end, to write it succinctly, it's this left of x. Whatever x is, there's only one value of left of x. It's just that most recent red dot. So not all of these are left of x. They used to be when x was smaller. But when x gets larger, left of x gets larger also. It's always the left end of the current interval. It's that 3 in the case of that last problem, that a plus 3 delta x. But we want to go past all of the full intervals to the beginning of this current interval. That's what left of x does for us. And how long do I use it for? Well, how far is x from left of x? Just subtract. So this is the entirety of a generalized approximate accumulation function. It is a function because I didn't mention a specific input x like 6.75 or something like that. It also, I didn't have a specific function r that I evaluated or a fixed number of intervals. So what I've got is a whole bunch of rates times delta x. How many of them? Well, it depends on what x is. And then I've got one term, and this is always going to be one term, that we use this abbreviating left of x in. And again, left of x can be written in terms of that a plus j, like that whole like a plus floor function expression times delta x, but that's really messy. So we just abbreviated it there, x minus left of x. So I have one term that involves this last interval's x value that I use for a different length of time. I don't know, like as x grows, this grows. Notice where there's x's in here. So delta x is a parameter, a is a parameter, j is kind of like a variable, but it's just, we count, j is a whole number counting thing, like 1, 2, 3, 4, etc. But this is a as a function of x. So x appears here. I've got left of x and x. So this gives us a spot on the x-axis specifically, and a spot that's a boundary point of intervals on the left axis. Inside the sum, there's no regular x's. There's just delta x's, which is a parameter. It's a width. X only appears up at the top. So as x grows, that sum stays the same most of the time. It will only grow when x grows enough to make that floor function result have one larger integer result. So this sum grows one chunk at a time, one extra term at a time as x grows. In between, this is the only part that's growing. So this part grows and grows and grows until it becomes a complete term. Essentially gets dumped into that. Once we pass every red dot, once we pass into a new interval, this last term starts again at 0 and grows from there, or shrinks. Like we could have negative rates in other cases. But this is all of how I can approximate accumulation based on knowing a rate function. And again, there's nothing that's like a specific to one particular type of function or size of anything. This is a general way to do this. So for any rate function, I can do this. For any x value, I could evaluate this. And the idea is, if I make delta x small, it's not even very much of an approximation anymore. The smaller I make delta x, the better an approximation this becomes, or the more exact it becomes. And in terms of writing this, delta x being small or large doesn't make writing this any harder or easier. For evaluation purposes, doing it by hand with small delta x's is awful. Doing this by hand with large delta x's is tedious enough. And we'll do a little bit of that on Thursday. We're going to look at something and have relatively large size delta x's and just go through like what all of the different pieces to this are doing for us. Because when you see all the symbols, like I said, I know it's overwhelming because there's a lot of symbols and it's very general. But we're going to go back to the beginning and go through a little bit faster on Thursday, and then we'll do a practice where you get to like try plugging in specific functions, specific numbers, and see how this works, what sort of results you get and what each of those results, like for different pieces of this sum, mean in terms of a specific application. So I'll stop at that for today. I think that's enough brain melting for one day. But I'll give you a part in the book to look over and see some examples of this worked out, and I will see you on Thursday.